that I have, with the recording, like whatever I do here, that's also posted on Canvas. Let's get started unless you have questions. All right. Let's see. Elma, are you there?
Yes, ma'am, I am.
Could you start us off with prayer, please?
Yes, ma'am.
Thanks.
Dear Heavenly Gracious Father, Lord Jesus, we thank you, we praise you for giving us this opportunity to be able to learn today. Oh Lord, we thank you that you kept us all safe and you kept us all healthy. Oh Lord, I pray that as we're learning today, Lord, help us to, Lord, at least be able to understand, oh Lord Jesus, in the midst of all the chaos and everything that's going on. Oh Lord, we thank you and praise you in Jesus' name. Amen.
So let's look at this. And by the way, I have sapling for this already posted, so you can start looking at it a little at a time. And that's due the 10th or probably the 11th. Okay. And we'll see. I might postpone it to like Monday or so. We'll see. All right. So what have we seen so far? Now we have finished our exams, part 1, part 2, as many parts, right? Now we need to start thinking about chapter 18 and then start reviewing. So what have we seen so far? Delta S universe is delta S system plus delta S surroundings. Okay. And we also know that delta S universe has to be positive for a spontaneous reaction. Spontaneous reaction. Now, instead of looking at delta S universe, they are going to come up with another parameter or function. And then we say delta G is the one that determines the spontaneity of a reaction. Okay. And of course, delta G will be directly related to delta S universe. Now, also, I need to remind you that delta S, maybe it's coming up in the next page, so I'll wait. Okay, I'll wait. So Willard Gibbs, 1870, he defined a new state function. Okay, now again, recall. This is a property. We talked about this in an analogy used was, you're on an elevator and if you want to get from the first floor to the 8th floor, you can either get there using the elevator, go straight from 1 to 8, or somebody can go from 1 to 3 and 3 to 5 and 5 to 8. Okay, it doesn't matter what steps you take, or you can take the staircase all the way to the 8th floor. All that matters is you were on the first floor, and then finally you're on the last floor, okay, or the 8th floor. So state function is that. It depends only on the current state of the system. And it also depends on where it came from, but not how it came to the current state from the initial system or the initial state. This is called as, of course, he has to introduce his name, Gibbs free energy. Okay, G. Entropy, enthalpy, those are Greek terms, but this is after his name. Gibbs free energy is related both, okay, we'll see how it is related, to the enthalpy change, that is delta H, right? Change is delta. And what's the other one? Entropy change, delta S. Okay. And delta S universe was already related to the enthalpy change, but they're putting it all together just to make it more convenient. Okay. So here they're showing the relationship. Delta S universe surroundings. Okay. Surroundings. And delta S surroundings remember we did problems. Okay, we were discussing about YT is in the denominator and such. That's where we left. Okay. So delta S universe, so it's all related to what's happening in the system. It's easier to measure what's happening in the system versus the surroundings. Okay, we have more control over what's happening in the system. So the substitution. Okay, now this is not rocket science, but they say multiply the whole thing by minus t. All right, so I multiply this by minus t. T delta S system minus, okay, minus t. And I put another minus here. This becomes plus, and the temperature cancels out. And I have this, okay. So they removed the t in the denominator and they multiply the whole thing by minus 1. So I can rearrange this. Minus t delta S system. All right, I just wrote delta H first and then delta S. Okay, Gibbs has done a lot of other things. So he now calls negative delta S universe he's going to give his own notation, and he's going to call this delta G. It's delta G. So the next page. According to the second law, delta S universe, what did we say about delta S?
Positive.
Positive, right. I'm just going to put a big sign for a spontaneous process, okay? So if a reaction should go, then delta S universe must be positive. But now what are we saying? Delta G is minus T delta S universe. Delta G then must be what? All the math whiz in the class and other students, everybody. What goes in the blank? Huh?
Must be negative.
Must be negative. Because this has to be positive for it to be spontaneous, but we're saying delta G is minus that. So this has to be negative. So this is our golden rule. We don't look at delta S universe. We take care of, we use delta G that has the T component in it. And so the formal definition, which you will use in organic, in biochemistry, in biology even, biological systems follow this. And T is, of course, in Kelvin. So T cannot be negative. Okay? So this is our golden rule. So delta S universe has to be positive, but delta G has to be negative for a spontaneous process. For most chemical reactions, the ones we do in the lab, unless you heat something, and even then you heat it and you maintain it at a certain temperature and you study the properties. So we do it at constant temperature, and of course we don't cook it in a pressurized system. So it is at constant pressure. So this is our equation. Standard conditions. Remember, we have the delta H with a 0, delta S with a 0. Standard conditions. Here, the temperature has to be 25 degrees centigrade or 298. Always remember to convert it. And pressure is 1 atm, okay, room pressure. For gas laws, when we said STP, that was 0 degrees centigrade, okay? But for thermodynamics, standard is 25 degrees centigrade. Okay, so for a reaction to be spontaneous, now you have to know these signs. We had problems with endothermic, exothermic, remember? So delta G less than 0, that also means that it is negative. If delta G is negative, what does that mean? Is it spontaneous or non-spontaneous? Spontaneous. Okay, spontaneous in the forward direction. So if I have A, and A is in equilibrium with B, okay? If delta G is 0 or minus something, then it's spontaneous in that direction. But in the opposite direction, it will be non-spontaneous, okay? So you need to keep that in mind. But in the forward direction, an increase in delta G, which means delta G here is positive, indicates a non-spontaneous reaction in the forward direction. So we have to be very clear. And at the end of the chapter, we'll also link delta G with capital K, equilibrium constant.
Dr. Mary,
Yeah. Yes, Kevin.
shouldn't that be in the reverse reaction?
No, delta G is positive. This is another reaction. If going this way, delta G is positive, then this is not going to happen that way spontaneously. Yeah?
Yeah.
Okay. Now, when it's neither negative nor positive, and we will use this also a few slides from now, the system is at equilibrium. Okay. So in the above cases, it's either highly product favored or reactant favored. Okay. Reactant favored, highly reactant favored, that means it's spontaneous. Okay. Spontaneous is nothing but product favored. I don't know what I said, but spontaneous is product favored. Same thing. Non-spontaneous is reactant favored. So you can relate to what you've learned before. And if it's right in the middle, it's in perfect equilibrium. Now I think you'll need your appendix A2 because I was not able to print it, and it prints like without any columns and things. So I'm going to give you a minute to go grab that, or if you want to. I tried printing it again and printed the first page. Okay, they're like 5 pages or so. Second page came out without any columns. Maybe I should take a picture of the screen. Or you can find any table online. Okay, you can find it, a thermodynamic table with delta G, delta H, delta S online. The values may be slightly different. So we are going to calculate delta G for this reaction. Now, remember, this is a gas here. So you have to look up correct values. And then what did we say? Delta G is, I think we did this problem before, so I might have values. Delta G 0 because it's at 25 degrees centigrade. Whatever values you get from the table, from the appendix, that's, trying to write straight here. That's at 25 degrees centigrade. Values of delta HF0, S0, delta GF0. These are all at 25 degrees centigrade from the table. Now, I have delta H0, we calculated it the other day, and this is negative. So forming water from hydrogen and oxygen is exothermic. And then I have the negative sign already. And temperature is 298. Delta S0 is minus 89.0 joule per Kelvin. Now this is in joules, so you need to convert one to this to kilojoules or this to joules. So I'm going to convert this to joules. 1,000 joules is 1 kilojoule. Okay, the units have to be the same. It doesn't matter which one you convert. Let me know what you get. And then tell me if this is spontaneous or not. I got to specify the temperature at 25 degrees centigrade because it's 298 Kelvin. Make sure you do the negative, take care of the negative values carefully. Or use the negative values carefully. Anybody with a number? Your answer will be in joules. Everybody's sleeping or working?
I got negative 457,078. So 457,078.
Okay, 3 sig figs is good. Is it 10 power 3 then?
Yes, ma'am.
Okay. 1, 2, oh, 3.
No, I think it'd be 5.
Oh, yeah, that's right. Yeah, you're right. All right, that is the correct answer. So the question is it spontaneous or not? Delta G is negative, so is it spontaneous? Yes. So what does that mean? Hydrogen and oxygen react to form. Okay. So thermodynamically, we say this is spontaneous. Which means it takes off. Okay. Everybody did the math? Okay. But what else does it say? The reaction of hydrogen and oxygen is a very large negative value. Okay? It's that much in kilojoules. So thermodynamics tells you if a process is spontaneous. And when does it say that it is spontaneous? When delta G is less than 0. Okay. However, in order to trigger the reaction, now when hydrogen, in a cylinder and oxygen in the cylinder, they come together, they're under a lot of pressure. So explosions can happen. But if it is controlled, you need a spark to start off the process. Why? Remember kinetics? This reaction has a very high activation energy. See that? So there is a kinetic control and a thermodynamic control. Thermodynamically, it says, yes, let's keep going. Kinetics, it's like, well, I have a high mountain to climb. See that? So they have to, if you're setting up a lab and you're trying to make a lot of, let's say, fertilizer, ammonia is a process that they have to take care of a lot of parameters to make it successful, in the sense that you are able to get more products within a short amount of time. It does not present any information about the rate. So thermodynamics, he operates on his own time. And then you have kinetics. So for us to make it worth our while, thermodynamically it has to be favored, and then kinetically the activation energy should not pose a problem. Got that? So there's the kinetic effect and the thermodynamic effect. Now, I have a video, I'll show it to you. The same goes for converting carbon diamond to carbon graphite. Now the delta G for this is a small negative value. What does that tell you? Is it spontaneous? Watch out for all those diamonds you're wearing. Delta G tells you that this is spontaneous. But what's the problem here, which is good for us? Kinetically, very. So, see that? Sorry, this pen is not the best. Okay. So we have to look at both kinetics and thermodynamics. All right. So free energy of formation. Now you can also use a table. And I'm going to let you do this for H2 gas plus O2 gas, giving 2H2O gas. I think there's 2 here. Now you will see a column, delta G F0, okay, free energy of formation. Just like you had delta H F0, you have delta G F0. Now you need your table for this. Can you pull up your table? Okay, I don't know what I'm doing. Let me pull up the appendix. Okay, you able to see the table? Okay. So you have delta HF0 and then delta GF0, you see that? And then S0. So go down here and find out what the values are for hydrogen gas, H and then O. So it's a long table. Did I pass H? Okay, hydrogen gas, okay, because it is formed, it is an element in its natural state, delta HF0 formation, and for the enthalpy of formation and the free energy of formation, those values are 0. And then for water gas, write these down, we need delta G. That's the second column. So it is minus 228.6. kilojoules, okay? And then for oxygen, it'll be the same as for hydrogen because it is an element in its natural state. All right, now I'm going back to, well, let's see if there's anything else I want to show here. I'll try to be quick. Okay, this is the video, I mean the example that I was showing you. Look at carbon diamond going to graphite. It's a small negative value, right? So it says that it is spontaneous. But then the question is that going to happen right away? Is it instantaneous? But the activation energy for this problem, for this conversion, is so high that it takes a very, very, very long time. Okay. So this is graphite, of course, and these are diamond. And structurally, you can look at it, structurally, these two are different. They're all carbons, carbon atoms, okay? You see the graphite, those are in layers. You'll see at a point in time. You see the layers now. Diamond extends three-dimensionally. And then the other one is don't know how to zoom it in here, but how we talk about ATP as the storehouse of energy. So ATP, when energy is needed, forms ADP, and this energy is released, okay, in the reverse direction. And then while he's waiting for another, to help another system, what does he do? He recharges himself, okay? So he picks up energy from different sources, and then he becomes ATP. And then he waits like a charged battery. He waits to help out a non-spontaneous reaction in the biological system. And then while he's waiting, he recharges. See that? So that's all that has to do with delta G. So when you do biochem, you'll be talking a lot about delta G and spontaneity and the equations and such. Those are the ones I think that I have for one. This is coming up, so I'll come back to it. Okay. All right. Chat. Yeah, that's okay, Brandon. Now I have to go back and share your. All right. Okay. So what answer do you have? Products, you have 2 moles of water. And what was the number that I gave you?
Negative 228.6.
Thank you. And that's kilojoules per mole. Okay, close up the brackets. Negative. And you have 2 moles of water. I'm sorry, hydrogen. And then a negative sign for the oxygen. You have 1 mole of oxygen. Times delta GF0 for oxygen. Okay. Now we said that's 0. Okay. Reason, elements in their stable state at or under standard conditions have delta HF0 and delta GF0 set to 0. All right. Conceptual question. So you have 2 moles here. Let me write very quickly in a little way. And can you give me an answer in joules?
I got negative 457,200 joules.
Okay.
Negative.
Can you give that to me in scientific, please? It looks
It's
correct.
yes, ma'am. It's 4.57 times 10 to the 5.
Okay. So that's the same answer we got when we did the problem, right? I'll wait for everybody to finish. This is the same answer we got when we used this equation. See that? Slide 52, we used this equation, we got the same result. So for delta G, you can calculate it using this equation. So I'll specify on the test, you should use this, using the formation of, I would say, using delta GF0 values, calculate delta G0 reaction. Or I'll say, using this equation, delta G equals delta H minus T delta S, calculate delta G0, all right? But both, if done correctly, should give the same numerical value, okay? Now I'm gonna set this up and then we'll keep going. Now you'll need delta GF0 values from the table. Let's see how we do this problem. Products first, right? Products first. So 3 moles CO2 gas plus 4 moles times delta delta GF0 water. Now water is a liquid here. They can give you gas or they can give you liquid. Now next comes our reactants. 1 mole times delta GF0 or C3H8, and this is propane. Okay, you have propane tanks for grilling. And I'm going to put another negative sign. I'm going to make it simple, like all negative for the reactants, positive for the products. Okay, 5 moles times delta GF0 for oxygen. Now, what did we say about oxygen gas?
It's 0.
It's 0, that's right.
Hey, Dr. Mary, I have a question.
Yeah.
Why did you subtract the 5 moles of oxygen from the 1 mole of the C3H8 gas?
See, this is the same as I opened up the brackets. So if you have A minus B plus C, this is the same as A minus B minus C, right?
Yes, ma'am. I didn't know you opened up the brackets. Thank you.
Yeah, I think this is easier to see. So all of your reactants, just put a negative sign in front. And if you want to do it the other way, that's fine too. Okay. So now I'm going to give you the delta GF0 values. For CO2, this is negative 394.4 kilojoules per mole. Next one, plus 4 moles. Delta GF0 for water liquid. Okay, you got to be careful because there'll be a different value for steam. And I need one more because the last one is, see now this is a reactant, so I made it negative. And this is only 1 mole. And this is minus 234. I'm sorry, 23.4. And they're all kilojoules, so you can keep it as kilojoules. I mean, know what you get. Is this reaction spontaneous? If you open up the tank, there's already oxygen in the atmosphere. Does it burn? Of course, you need a spark. You see that?
Dr. Mary.
Ah, yes.
So is the one for let's see,
Propane, yes.
the last one is like negative.
Mhm.
The number is negative in the last reactant.
23.4.
So the negative sign in the beginning is
Yeah.
like,
That should be there. That's a negative sign. Yeah, negative.
no, the other one.
This one?
Yeah.
Negative. Tell me what you get.
I got negative 2.11 times 10 to the third kilojoules.
Mm, 294.4 to 71.1. What did you say? 2.11 times 10 power 3?
Yes, ma'am.
Now I have 2.03 times 10 power 3 kilojoules. So it's okay because we both have the same numbers. That's why I was trying to see if I wrote everything down correctly. 23.4. Either one is fine. Okay, but this is what I have from that because I'm just using the answers unless they made a mistake. All right.
I got what Kennedy got.
Oh, she did. Okay. So we'll go with that. They must have made a mistake. All right. So this is another problem, okay, where you use delta GF0. Now for the same problem, if I gave you delta H and delta S, and you should be able to use the equation. Okay, and you'll get the same result. Should get the same result. With this, sorry, equation. That's good. Okay. When I don't specify or when Sapling doesn't specify, then you can do it either way. All right. Next, we're going to talk about the same equation, but for a solution. Okay? For a solution. If I have a solution, or let me say this. Did you all write that down? This is the next example. I have ammonium chloride, okay, solid. I'm dropping this in water, a teaspoonful. And then what will it do? What will ammonium chloride do when I put this in water? We don't care what it does. What does it do? What happens when you put sodium chloride in water?
Dissociate.
It doesn't like,
Dissociate.
it will not dissociate because both of them come from a strong base and a strong acid.
They will always. This is based on solubility. It doesn't have to. You're answering the question as to whether the solution that you get is acidic or basic. All your salts, as long as they are soluble, according to the solubility chart, they will dissolve. So when you put ammonium chloride, all ammonium salts are completely soluble in water. So when you dissolve that in water, what would you see if you were able to see what's in water?
NH4 plus and Cl minus then?
Yes.
But Dr. Mary, how come we said before that Cl minus is not reactive? So it will just dissociate?
No, yeah, they will all dissociate. Okay, they will all dissociate, and then you're seeing what Cl does and what ammonium does. You see that?
Oh yeah, I understand now.
So this is the primary step, and after that you're looking at each ion individually. Okay, good question though. So now we are looking at the primary process. You don't know too much these days. Dissociation. Okay. Now this dissociation delta H for this is positive. What does that mean? Delta H is positive. What does that mean?
That is
It's
spontaneous.
spontaneous.
Delta H, not delta S.
Oh, that it is exothermic reaction.
Delta H positive, is that exothermic or endothermic? Here's where we, endothermic, right?
Endothermic.
So remember the signs. This is endothermic. What does endothermic mean?
Absorbs heat. Like it doesn't give out heat.
What does it do then?
It absorbs it.
Absorbs heat. Okay, it absorbs. You remember you add heat on the reactant side. So delta H is positive. Now I'm going to write this again. You don't have to. What about delta S? Just a sign. what about change in entropy? Is the entropy increasing or decreasing?
It's increasing.
Increasing. Okay, we were busy studying chapter 17, right? Increasing.
How do we know that based on delta H? Is it just like are we just supposed to like know it
Oh
from the
no,
formulas you gave us?
delta H, that will be given to you. Okay.
But it's just because it's going from a solid to an aqueous,
No,
right?
she's asking about delta H.
No,
Oh.
I was asking how delta H is in a relationship with delta S.
We're going to come to that after we look at delta S. They are not related. So delta H can be positive, and the delta S for the same reaction can be negative or positive. You see that?
Okay, so how did you know that the delta S was like was increasing?
Okay, so remember we looked at examples where if you have a solid and it's going to solution, think about the solid. It's all structured, right? What happens when it
Yes,
becomes ions? They're all breaking down and they're distributed.
they become, yeah.
Mhm.
Okay,
So
thank you.
that's why, yeah. So this entropy increases as you go from solid to ions in solution. Just like going from solid to liquid, it's the same thing, similar. So if entropy increases, you have to remember the sign. This is positive. Okay. Now, the thing is, you have to put this together to know if the reaction is spontaneous. Delta H is positive. You see that? So ultimately, it depends on, this is positive. There's always the negative sign. T is always positive, and this is a positive value. Okay. So for the whole reaction to be spontaneous, your delta S value has to be large enough to make this whole thing more negative, okay, mathematically. So let's take this in steps. We got to look at this equation.
Dr. Mary, theoretically speaking, we cannot determine delta G values, like signs, just like that.
No, you have to, yeah, exactly. That's right. So you have to look at delta H and delta S. And because delta G by itself, unless you have like the delta GF values, and then you can calculate, but otherwise to know if a reaction is spontaneous or not, then you have to consider the delta H magnitude and the sign, and the delta S magnitude and the sign. Okay, good point.
Okay.
All right, so just hold on here. We're going to break it down some more in the next few slides. Free energy and entropy, they are also relevant to the formation of solutions. We talked about that. Now, I thought they were using ammonium chloride. That is also endothermic. Ammonium nitrate. This is used in cold packs. Okay, how does it work in cold packs? This is highly endothermic. Highly. Okay. What does it do? Why does your hand turn cold when you like crush those things and you let it go in solution? Why does your hand turn cold? Why is it a cold pack? What is happening? Anybody?
It's absorbing the heat
From where?
from your hands.
That's right. Okay. Where is this heat coming for this? From your palm. See that? So you're doing something. How does to get the cold pack effect? You're doing something that removes heat from that specific area. See that? So delta H is large. I'm going to call this, I'm going to give it a number. I like to give numbers. 1,000, no, let's make it 100 kilojoules. Okay. I'm just making up numbers. So they're saying this is very effective and that it requires quite a bit of heat to break it into ions. Everybody with me? Yes. Even those that are sleeping? Yes. Okay. Now, that's not the only factor that'll decide if the reaction is spontaneous or not, okay? So the other factor is, we already talked about these things, so it's going in slow motion. The particles in the solid ionic compound, okay? Think about the solid. It's like a cube with all the ions, you know, in place. We can have the ammonium ion here, the nitrate there, okay? It's an example of a solid structure. All the ions are in place. Now, when you put this in water, they're like, I don't want to be near you. I don't want to be near you. I don't want to be near you, okay? There's a lot of social distancing right there when they go in solution, okay? And the particles in the solid ionic compound are highly ordered, right? The crystalline structure is highly ordered and very close to each other. More importantly, we care about the ordering here because delta S is a measure of randomness. But once you throw it in, you know, your spoon full of sodium chloride goes into solution, these particles, they run away. As much room as there is in the container. So now there's a tug of war. Well, between numbers, okay? T is always going to be positive. What about the entropy? Is sufficient to overcome the positive enthalpy changes. So overall, you do see the particles going into solution. Whether it's cooling your hand or not, it's going into solution. So that is a spontaneous process. So let's plug in our fake numbers here, 100 kilojoules. Minus T, let's make that 300 Kelvin. Okay, I'm just picking some numbers here. Or 298. Now my delta S, see this is already 100, so I'm going to make this 1 kilojoule per Kelvin. Okay, delta S is 1 kilojoule per Kelvin. So let's look at the ultimate result. Yes, it did cool your hands quite a bit. Because this is multiplied by temperature, this guy ultimately wins. Because it makes the whole thing negative. Sorry, I don't like this pen. Okay. So we are going to see cases in the near future where temperature will play a big part. Let's say the temperature here dropped to like 50 Kelvin. Okay, let's say the temperature dropped to 50 Kelvin. Then delta G will be positive. You see that? So in some cases, your temperature will play a role, and that's what we're going to look at next. Any questions? No, you good? Okay. Oh, we have actual values. I didn't see that. Okay. Let me give you actual numbers. Are they asking you to find delta H0 and delta S0? You can do that, but I'm going to give you delta H0 values, 14.0 kilojoule. Okay. And delta S0 reaction. You'll have a worksheet, by the way, on Thursday afternoon. Now this is 73.2 joule per Kelvin. Both are positive. See that? This is favorable. Delta S is positive. Delta H is endothermic. Now, we do the dissolution at 298 Kelvin. The question can be, is the reaction spontaneous or not? And only delta G can tell you if the reaction is spontaneous or not. Okay, so can you calculate delta G? Okay. So I'm going to convert this to joules. Just multiply by 10 power 3, that'll become joules, minus, see, multiplying by this temperature makes a difference. 73.2 joule per Kelvin. What is the answer? We know that it does dissolve, so delta G must be negative, but what is the answer that you get?
Negative 7,813.6.
Okay, so let's do 3 sig figs and scientific. What is it, negative? 7.8
Yes, ma'am.
times what?
10 to the 3.
Joules, okay? So,
Dr. Mary.
uh-huh.
So if we had kilojoules and joules, the answer, we would rather have the answer in joules than kilojoules.
No, it doesn't matter. On the test, I'll specify, but
Okay.
if not, you can change, you can keep it all in kilojoules, or you can keep it all in joules, it doesn't matter, but they all have to be the same, okay?
Okay.
All right, so we're gonna look more into this. And we are at 11:49. I think I'll go until 12:15 or before, okay? I just have a few more pages. And it's going to be in relation to what we've talked about so far. I'm looking for the other pens that I had. Anyway, free energy change and temperature. So we are going to look at this some more. Okay. T is going to be a deciding factor in what we are going to do next. Now, if you want your reaction to be spontaneous, delta G equals delta H minus D delta S. Mathematically, what will favor what signs of delta H and delta S will favor the reaction? If you have a negative delta H, right, mathematically, if this is negative, and that is positive, then delta G will be a big negative value and positive. Okay, so put on your math thinking cap here a little bit. So when both quantities are favorable, okay, so this is the favorable sign conditions. So if this is minus 100 kilojoules, this is always positive. This must be positive, so this will be negative. And let's say 10 kilojoules. Okay, that's the most favorable situation. And when neither quantity is favorable, when does that happen? When delta H is positive and delta S is negative. See that? When delta H is positive and mathematically, delta G will be positive. So here you cannot do anything. You cannot, you can even stand on your head. It's not going to change anything. Okay. When one quantity is favorable but the other is not, so here delta H can be positive, and delta S is also positive. And another condition when delta H is negative and delta S is also negative. Here the actual values become important. Like in the previous case, delta H was not that big, okay? So it depends on the magnitude of the parameters. Temperature and the magnitude of the parameters will determine if the reaction is spontaneous or not. Okay. Depends on the temperature and the magnitude of the parameters. What are the two parameters? Delta H and delta S, of course. So that's what you're going to look at. Power play. Who's bigger? What's the temperature? Okay. Temperature plays a big role. It's repeated here. So remember, this is the highly favored situation. Reactions spontaneous. At all temperatures. Okay. At all temperatures. Because this combination gives you a negative delta G. And if this is positive, remember T is always positive. Because it's written in Kelvin. You can fill that in. I want to leave it blank so there's less information for now. Now this is a bad scenario. Delta G, no matter what you do, will make the reaction non-spontaneous, no matter how low the temperature is, even at 0 Kelvin. Okay. Negative and negative. So here is where temperature plays a part. Temperature role is vital. Okay. So here, this depends on the magnitude, right? This could be plus or minus. I'm going to write it like this. Spontaneous at low temps. Okay. Spontaneous at low temps. So it's negative or what happens for the same reaction if you increase the temperature, non-spontaneous at high temps. Okay. Non-spontaneous at high temps. Here it's going to be the opposite. Spontaneous at high temps, non-spontaneous, low T. I'm going to look at that, okay? How is that possible? Make sure it's still recording. No, there are two chats. I didn't see it. Okay. Now, in case we look at this case, okay. Delta H, remember I'm looking at this scenario, the negative and the negative. And if I do that, then you can, understand that one as well. So here, delta H is going to be, I'm going to use my spontaneous at low temp. Low temp. So this is let's say it's 25 kilojoules. Okay. And it depends on, you can adjust the temperature, but for a reaction, the delta H and the delta value, S values are set, right? But the magnitude of these values are important as well. So at low temperatures, I'm just going to go with the flow and see. I don't know if the numbers will work. Delta G is minus 25 kilojoules. I made both kilojoules minus. Let's say the temperature is 100 Kelvin. Okay. Multiplied by minus 2 kilojoules. It's not going to work, right? It's 200 and this is 25. So let's make this 250 kilojoules, guys. Let's make this 250 kilojoules. I'm just playing with numbers here. This is at low T, which is 100 Kelvin. Minus 250 kilojoules minus plus 200 kilojoules. Okay. So at low temperatures, this is spontaneous. All right. What happens at high T? I'm going to increase the temperature. At high T, let's make it 200 Kelvin. Let's do the math again. Because delta H and delta S, they don't change for the reaction. They're always the same. You can only play with 200. Play with the temperature. So this still remains the same. Delta S also remains the same, but the temperature, you've made it higher. So now this is positive. Okay, so for a reaction, oh, don't like this ink. I'm so sorry. Get my money back. This is 2 kilojoules minus 250. This is plus 400. Okay. Non-spontaneous at high temperature. Now you can use similar analogies or similar values and prove, okay, prove this case as well. And these are both positive. You can test it and you will see that at high T, okay, at high T, this will be negative because your delta S will be a large positive value. And then at a low T, it will be non-spontaneous. That'll be our last slide for the day. Now they want you to calculate delta G for this reaction. I wouldn't say a reaction, it's a phase change. TiCl4, liquid becomes gas. Find delta H, zero reaction. Okay. Now I'm going to ask you to find your appendix. Can you find your appendix and give me values? Why don't I do this? I'm going to mark this as homework for Thursday at 1:30. Okay. I want you to find delta H0 reaction. I need to see the calculation. Delta S0 reaction. And then delta G0 reaction at 298 and at 775. Okay. Homework, and you'll be showing your work to me at 1:30 via phone or Zoom. How about that? I want you all to go back and think through and not overload. I don't want to overload your brain at this time. All right, any questions though? Last minute questions? Everybody doing good?
Yes.
Yes,
Yes,
Yeah.
ma'am.
staying safe. Okay. So we're almost at the end of the semester. And like I said, on Thursday or by Thursday afternoon, I'll have a plan for the next 2 weeks. Okay. So I want you to review this part. So you do this homework while it's still fresh, and then also study for your quiz, your lab quiz. And then lab for this week, you just have to turn in the post lab for the qualitative analysis, I think, whatever is on Canvas. All right. Okay.
Hey,
So
Dr. Mary, I have a quick question.
Yeah.
What is, on the homework that you just gave, what is the 14.0 kilojoules? Like, where did you get that from?
If you do the calculation here, which is missing, your final answer is that.
Okay, thank you.
Yeah. And you have to use the table, okay? You can use any table that's available. All right. Any other questions? And I have to get busy, grading all your tests as well. I'll do that this weekend because we don't have class on Friday. And that's what I'll be doing. All right, guys. Have a nice afternoon. It's really nice out here. And I'll see you all Thursday at 11. Zoom session. And you'll not be allowed your notes, just your equations and any tables that you need, I will post again. Okay? All right. Bye, guys. Stay safe.
See you later, Dr. Mary.
Bye,
Bye.
Dr. Mary.
Take care. Nice seeing you all.
All right, we'll see you Thursday then.
All right.
Hey,
Bye.
Dr. Mary, when is this going to be posted?
What's
The
your
recording.
like this afternoon? I have a class right after at 12:30. So by 5, I'll post it.
Okay.
Does
Because
that
I
sound-
missed some of the first part.
Oh, you did? Okay. I'll try
Yeah,
to
it
post
was-
it soon. What I'll do is, as soon as we are done here, let me stop recording first.